Hi everybody, welcome to another session of Nero. I'm Srijit here. Today I'm continuing the band gap analysis using our AMS band module. So in this session, I'm just focusing on how we can analyze the density of states using this molybdenum disulfide example. So in the previous session, I have briefed you how we have calculated the band gap. So for molybdenum disulfide, the band structure reveals the valence band and the conduction band, and also the energy difference between the top of the valence band and the bottom of the conduction band is the band gap. So in the case of a monolayer molybdenum disulfide, which has a direct band gap of around 1.8 to 1.9 electron volt, or in the case of bulk molybdenum disulfide, which has an indirect band gap of around 1.2 electron volt. So this difference in band gap is crucial for the distinct optical and electronic properties. So the shape of the bands indicate the effective mass of the electrons and holes, which influences their mobility within the material. So the density of state. So let me show you what is actually the density of state. Just I'm taking this example, the typical example. Okay. So you can see this is actually the density of state image. Before going into that, must focus on that how the AMS band can calculate the density of state, which represents the number of available electronic states in each energy level. So then the density of the density of state plot for molybdenum disulfide shows peaks of energies corresponding to energy bands. A region with zero. Let me show you. The region with the zero. You can see this is the region with zero. It indicates the band gap where there is no allowed electronic states. So this is actually the region with zero. And the density of state near to the band edge is particularly important as it influences the probability of electronic transitions and the material's conductivity. And the sharp peaks in the density of state near to the band edges, actually this is actually the band edge. So the sharp peak near to that band edge of molybdenum disulfide indicates the localized electronic states that play a critical role in its optical properties. So this projected density of states or the periodic density of state VDOs can further reveal the contribution of specific atomic orbitals. For example, I will show you from the previous image. So this is actually that typical example of this periodic density of state, because in the case of molybdenum, d orbitals, and for sulfur, p orbitals are taking part in this specific calculation. So that's which we can see here. And coming back to this picture, let me continue. So the PDOS can further reveal the contributions of specific atomic orbitals to the overall density of state at a different energy level, providing insights into the nature of chemical bonding and electronic transitions. And also, the factors affecting the energy of state in molybdenum disulfide can be studied using AMS band. So the number of layers. For example, in AMS band can model the molybdenum disulfide with varying number of layers, demonstrating the transition from an indirect band gap in bulk to a direct band gap in the monolayer molybdenum disulfide due to quantum confinement effects. And speaking about the strain, applying strain to molybdenum disulfide alters the atomic distances and thus the electronic band structure and band gap. Then the AMS band simulations can predict how different types and magnitudes of strain tune the energy states and optical or electronic properties of molybdenum disulfide. So in the next, I'm just right now winding up this thing because it is a lengthy session. So in the next session, I will be focusing on how we can focus on the factors that affects the energy states of molybdenum disulfide using AMS band. Thank you.